Rosalind Franklin was born in London in the year 1920 into an educated and influential Jewish family. From an early age, she displayed an extraordinary aptitude for science and mathematics, far exceeding the abilities of her peers. Her father, Ellis Franklin, was a banker who valued education but initially discouraged her from pursuing a career in science. The societal expectations of the time made it difficult for women to gain recognition in scientific fields. But Rosalind was determined to overcome these barriers. She attended St. Paul's Girls' School, one of the few institutions that provided a rigorous science education for women, where she excelled in physics and chemistry. Encouraged by her teachers, she decided to further her education at Newnham College, Cambridge, where she studied natural sciences. At Cambridge, Rosalind was drawn to physical chemistry, a discipline that focused on understanding the structures and behaviors of molecules. Her meticulous approach to research and her relentless drive for precision set her apart from her fellow students. Despite her evident talent, she faced a scientific world that was largely dominated by men, where female scientists were often overlooked or dismissed. This reality only fueled her determination to succeed, and she worked tirelessly to prove herself through the quality of her research. In the early 1940s, she completed her degree and continued at Cambridge to work on coal and graphite research, an area that would later prove crucial in her scientific career. She developed expertise in X-ray diffraction, a technique that would eventually play a pivotal role in her groundbreaking discoveries about DNA. The outbreak of the Second World War disrupted many scientific careers, and Rosalind turned her attention to applied research that would aid the war effort. She joined the British Coal Utilization Research Association, where she conducted groundbreaking studies on the microstructure of coal. Her research on the porosity of coal had important industrial applications, improving the efficiency of gas masks used by soldiers and civilians during the war. Her ability to analyze complex structures at a microscopic level refined her skills in crystallography and molecular imaging, which would later define her legacy. During this period, she published multiple papers detailing her findings, gaining respect in the scientific community. However, despite her growing reputation, the challenges of being a woman in a male-dominated field remained ever present. In 1945, she earned her doctorate from Cambridge, focusing on the physical chemistry of solid materials, but opportunities for women in British scientific institutions were still scarce. Seeking a more supportive environment, she moved to France in 1947 to work at the Laboratoire Central de Services Chimiques de l'État. Under the mentorship of Jacques Mering, she refined her expertise in X-ray crystallography and diffraction techniques, which were crucial in studying molecular structures. In Paris, she found a scientific community that was far more accepting of women in research than what she had encountered in Britain. She thrived in this setting, gaining confidence in her abilities and developing a reputation as a meticulous and innovative researcher. Her work in Paris further honed the techniques that she would later use to unravel the mysteries of DNA. By the time she returned to England in 1951, she had established herself as a leading expert in X-ray diffraction. She accepted a research position at King's College London, where she was tasked with investigating the structure of DNA. Unbeknownst to her, this new role would place her at the center of one of the most significant scientific discoveries of the 20th century. Upon arriving at King's College, she expected to have full autonomy over her research, believing she was leading an independent investigation. However, tensions quickly arose with her colleague Maurice Wilkins, who had been working on DNA before her arrival and wrongly assumed she was his assistant rather than an equal collaborator. This misunderstanding created an atmosphere of rivalry rather than cooperation, setting the stage for future conflicts. Despite these tensions, Rosalind immersed herself in her work, applying her expertise in X-ray diffraction to capture some of the clearest images of DNA ever produced. She developed innovative techniques that allowed her to refine the process, leading to the production of a now famous image known as Photo 51. This image provided undeniable evidence that DNA had a helical structure, an insight that would later become crucial to the discovery of the double helix model. However, as she meticulously worked through her data, she remained unaware that her findings would soon be used without her direct consent. As she continued her research, her relationship with Wilkins remained strained, and the competitive nature of the scientific environment at King's College made it difficult for her to share her work openly. Meanwhile, at Cambridge University, James Watson and Francis Crick were working on building a model of DNA but lacked the empirical data to confirm their theories. Unbeknownst to Rosalind, her research was about to be seen by those who would take a different approach to scientific discovery. Without her permission, Wilkins showed Photo 51 to Watson, who immediately recognized its significance. This unauthorized sharing of her work gave Watson and Crick a critical advantage in their race to decipher the structure of DNA. By the time Rosalind was close to reaching her own conclusions, Watson and Crick had already begun using her data to construct their now famous DNA model. While she remained focused on refining her findings, unaware of the full extent of what was happening behind the scenes, the foundation of her work was being utilized by others. The scientific world was about to witness one of the greatest breakthroughs in molecular biology. But Rosalind Franklin's name would not receive the recognition it deserved. Her journey, filled with intellectual brilliance and perseverance, had led her to this pivotal moment. Yet the full impact of her contributions was still waiting to be acknowledged. As the Second World War engulfed Europe, scientific research took on new urgency. Rosalind Franklin, having just completed her studies at Cambridge, found herself drawn into applied research that could contribute to the war effort. She joined the British Coal Utilisation Research Association, an organization dedicated to improving fuel efficiency and developing materials essential for wartime industry. At a time when many scientists were shifting their focus to weapons development, she chose a different path, working on the structure and properties of coal. Her meticulous approach and sharp analytical skills allowed her to make significant contributions in understanding how coal's porosity affected its performance as a fuel source. Her research had direct implications for the design of gas mask filters, a crucial defense against chemical warfare. By analyzing the fine structure of coal, she helped improve the efficiency of activated charcoal filters, ensuring better protection for soldiers and civilians. These advancements saved lives. Yet her work remained largely unrecognized outside scientific circles. Despite the practical importance of her research, the male-dominated field of physical chemistry offered her little acknowledgement. Even so, she persevered, publishing multiple papers on her findings, demonstrating an early ability to combine scientific rigor with real-world applications. During these years, she mastered X-ray diffraction, a technique used to analyze the atomic structure of materials. It was a demanding and intricate method, requiring extreme precision, but Franklin excelled in it. Her ability to interpret complex diffraction patterns set her apart from her peers. This expertise in crystallography, developed through her study of coal, would later become the key to one of the greatest discoveries in molecular biology. Though she had no way of knowing it at the time, she was already refining the techniques that would lead her to DNA. In 1945, with the war nearing its end, she completed her doctoral thesis, titled The Physical Chemistry of Solid Organic Colloids. It was a highly technical study, yet it laid the groundwork for modern material science. With her doctorate in hand, she sought new challenges. But in post-war Britain, opportunities for women in science remained scarce. Research institutions were still largely controlled by men, and despite her expertise, she found herself sidelined in many discussions. Unwilling to accept these limitations, she set her sights abroad, seeking an environment where she could work without the constant struggle for recognition. In 1947, she moved to Paris to join the Laboratoire Central de Services Chimiques de l'État, under the guidance of Jacques Mering, a respected scientist in crystallography. She continued refining her skills in X-ray diffraction. In Paris, she finally found a community that welcomed her as a scientist first, rather than viewing her through the lens of her gender. Unlike the rigid structures she had encountered in Britain, the research culture in France was more collaborative, and her talents were quickly recognized. She thrived in this environment, working on the structure of carbon-based substances and deepening her understanding of molecular organization. Her time in Paris transformed her scientific approach, reinforcing her belief in precision and meticulous experimentation. She published several influential papers on carbon structures, earning a reputation as a rising expert in crystallography. But while she was making significant strides, a new challenge awaited her, one that would change the course of her career forever. By 1950, her reputation had spread beyond France, and she was offered a position at King's College London, a leading institution conducting groundbreaking research on molecular biology. She was recruited to work on the structure of DNA, a field that was still in its early stages. The opportunity was irresistible, as it offered a chance to apply her expertise in crystallography to a biological problem of immense significance. In 1951, she returned to England, unaware that she was about to become entangled in one of the most controversial scientific rivalries of the 20th century. She entered Maurice Wilkins' lab, expecting to work independently, but from the start, there was confusion about her role. Wilkins, who had already been working on DNA, mistakenly assumed that Franklin had been hired as his assistant rather than as an equal collaborator. This misunderstanding led to immediate tension between them, setting the stage for future conflicts. Despite the strained atmosphere, Rosalind focused entirely on her research. She began refining X-ray diffraction techniques to study DNA structure, bringing a level of precision that had been lacking in previous studies. Her attention to detail allowed her to produce high-resolution images of DNA fibers, revealing crucial clues about their underlying structure. But she was methodical, unwilling to jump to conclusions before verifying her data. Unlike other researchers who relied on theoretical modeling, she insisted on gathering concrete experimental evidence. It was during this period that she captured what would later become the most famous X-ray photograph in the history of science, Photo 51. This image, taken in 1952, provided definitive proof that DNA had a helical structure. The distinctive X-shaped diffraction pattern was unmistakable. It was a revelation, the key to unlocking the secret of life itself. But while she meticulously analyzed her data, her rivals were growing impatient. James Watson and Francis Crick, two ambitious scientists at the University of Cambridge, were attempting to build a model of DNA. They lacked the crucial experimental evidence needed to confirm their theories, and their progress was slow. Then, without Franklin's knowledge, Maurice Wilkins showed Watson Photo 51. The moment Watson saw it, he realized its significance. He rushed back to Cambridge to share the findings with Crick, and together they used Franklin's data as the missing piece in their puzzle. Rosalind continued her research, unaware that her discoveries had already been shared with others. While she remained focused on refining her conclusions, Watson and Crick were racing to construct a DNA model based on her work. They took a different approach, relying on her data to infer the double helix structure rather than independently proving it. As they finalized their model, Rosalind was still conducting precise calculations to verify the dimensions of the DNA helix. She was careful, deliberate, unwilling to publish until she was absolutely certain. By the time she was ready to share her findings, Watson and Crick had already prepared their groundbreaking paper. In April 1953, they published their model of DNA in the journal Nature, marking one of the greatest discoveries in biology. But Rosalind Franklin, whose work had provided the critical evidence, was barely acknowledged. Her own research paper, which detailed the X-ray diffraction images and calculations, was published in the same issue of Nature, but as a supporting article rather than a central discovery. Though she had made the crucial observations, she was denied recognition. Watson and Crick's work was immediately hailed as revolutionary. While Rosalind's contributions were overshadowed, the credit had been taken, and she was left on the margins of one of the most significant breakthroughs in science. Yet, rather than dwell on the injustice, she moved on. She turned her attention to new challenges, shifting her research to virus structures at Birkbeck College, where she would make yet another impact in molecular biology. Her story was far from over, but the battle for proper recognition had just begun. Rosalind Franklin's research at King's College London was methodical and precise. She was not interested in speculation or quick conclusions, but in producing concrete experimental evidence. While other scientists rushed to develop theoretical models of DNA, she focused on refining her X-ray diffraction techniques to capture clearer images of its molecular structure. This careful approach led to a breakthrough in 1952 when she captured photo 51, the most crucial piece of evidence in the discovery of DNA's double helix structure. The image revealed a striking X-shaped diffraction pattern, a clear indication that DNA had a helical shape. Rosalind immediately understood the significance of the image, but refused to rush into premature conclusions. She wanted to verify the measurements, ensuring that every interpretation was accurate before announcing any major findings. Meanwhile, tensions with Maurice Wilkins continued to simmer, creating an uncomfortable working environment. Wilkins, who had expected to lead the DNA research at King's College, resented Franklin's independence and meticulous approach. Their inability to collaborate effectively would have lasting consequences. Unbeknownst to Rosalind, her careful and patient approach was about to cost her the credit she rightfully deserved. While she remained focused on collecting conclusive data, a competing research team at the University of Cambridge was taking a very different approach. James Watson and Francis Crick, two ambitious scientists attempting to model DNA, were struggling to build an accurate structure. They had theorized that DNA might have a double helix formation, but they lacked direct experimental proof to support their claims. Then, in January 1953, without Rosalind's knowledge, Maurice Wilkins showed photo 51 to James Watson. The moment Watson saw the image, he immediately recognized its significance. He realized that the pattern in the X-ray diffraction image provided the missing confirmation that DNA was indeed a double helix. He rushed back to Cambridge to share the discovery with Crick. They now had the key evidence they needed to finalize their model. But this evidence had not been obtained through their own experiments. It had been Franklin's work, shared without her permission. Rosalind, still unaware of this betrayal, continued her analysis. She worked tirelessly to refine her calculations, ensuring that the dimensions and symmetry of the DNA helix were correct. She was close to reaching the same conclusions as Watson and Crick, but she wanted her findings to be based on hard data, not guesswork. However, while she remained cautious, Watson and Crick moved quickly. Using Rosalind's image as their final piece of evidence, they completed their model and prepared to publish their results. By March 1953, Watson and Crick had built a three-dimensional model of DNA, one that incorporated the key insights from Rosalind's work. They understood that the two strands of DNA twisted into a double helix, held together by complementary base pairs. Yet, at no point did they acknowledge that their breakthrough had come from Rosalind's data. They prepared to publish their findings in the scientific journal Nature, positioning themselves as the sole discoverers of DNA's structure. Rosalind was still unaware of the full extent of what had happened. She had been working independently on her own paper, planning to publish her X-ray diffraction findings in the same journal. But before she could finalize her conclusions, she was informed that Watson and Crick's paper was already set for publication. She was stunned. How had they reached the answer so quickly when they had been struggling just months before? Only later did she realize that her own work had been used to confirm their model. Her years of research, her expertise in X-ray diffraction, and her cautious, precise approach had provided the foundation for one of the greatest discoveries in biology. Yet she had not been included in the recognition. She was not invited to present the findings, nor was she asked to collaborate. Instead, her paper would be published in the same issue of Nature, but as a supporting piece. Her findings would serve only to validate the conclusions that Watson and Crick had already announced. On April 25, 1953, Watson and Crick's paper, titled Molecular Structure of Nucleic Acids, a structure for deoxyribose nucleic acid, appeared in Nature. It was a moment that changed the course of science, yet Rosalind Franklin's name was barely mentioned. Maurice Wilkins also published a paper in the same issue, describing the X-ray work at King's College. But again, Franklin's contributions were downplayed. Her own paper, detailing Photo 51 and the X-ray diffraction results, was published alongside theirs, yet it was treated as secondary evidence rather than the foundation of the discovery. The scientific community quickly celebrated Watson and Crick as the pioneers of DNA structure. Their double helix model was hailed as a revolutionary breakthrough, and they received widespread recognition for their work. Rosalind, however, was left on the sidelines. She had provided the key experimental proof, yet she was not included in the recognition or the credit. She had played an essential role, but her contributions had been overshadowed by those who had used her data without acknowledgement. Though deeply disappointed, Rosalind did not let the injustice consume her. She refused to be defined by this betrayal and chose to move on. Rather than fighting for the credit she deserved, she turned her attention to a new scientific challenge. In late 1953, she left King's College and joined Birkbeck College, where she would begin her next major research project. One that would again prove to be groundbreaking. She shifted her focus from DNA to the study of viruses, an area that would eventually make significant contributions to medical science. But while she moved forward, the scientific world continued to celebrate Watson and Crick. Their names became synonymous with the discovery of DNA structure. While Rosalind's role remained hidden in the background, she had done the work, she had taken the photograph, and she had uncovered the evidence. But history was already writing her out of the story. However, her journey was far from over. She was about to make another impact on the world of science, one that would continue long after her untimely death. In April 1953, the scientific community witnessed a historic breakthrough. James Watson and Francis Crick published their paper on the structure of DNA in Nature, revealing their now famous double helix model. The discovery was hailed as revolutionary, a monumental step forward in understanding the molecular blueprint of life. Yet, in the midst of this excitement, Rosalind Franklin's name was barely mentioned. Her own paper, meticulously detailing her X-ray diffraction findings, was published in the same issue of Nature, but it was treated as supporting evidence rather than a key discovery. The structure of DNA, which she had painstakingly uncovered through her experimental work, was now credited entirely to Watson and Crick. The scientific community largely overlooked how Photo 51 had provided the final confirmation of DNA's helical structure. Instead, all attention was focused on the Cambridge duo and their theoretical model. Maurice Wilkins also published a paper in the same issue, describing the X-ray diffraction studies at King's College. While his findings had contributed to the discovery, it was Rosalind's data that had provided the critical proof. Yet, she received no formal recognition in the announcement. The circumstances surrounding how Watson and Crick had obtained her data were not discussed. No one questioned how they had so quickly confirmed their model just months after struggling to find the correct structure. For Rosalind, the moment was bittersweet. She had uncovered the key evidence, but she was not being credited for her role in the discovery. The reality of being a woman in science was clear. No matter how significant her work was, recognition was not guaranteed. She had seen it happen before, as many of her female colleagues had been overlooked or undermined by male counterparts. Still, she did not dwell on the injustice. Instead of fighting for credit, she made a defining decision. She moved on. While Watson and Crick basked in the glory of their discovery, Rosalind left King's College and accepted a new position at Birkbeck College in London. There, she would begin a new chapter, shifting her research focus away from DNA. She was determined to continue making scientific contributions, regardless of the recognition she received. At Birkbeck, she joined John Bernal's laboratory, a leading center for crystallographic studies. The environment was vastly different from the one at King's College. Here, she was respected as an independent scientist, given the freedom to lead her own projects. She quickly immersed herself in a new research area, virus structures. Her early work focused on the tobacco mosaic virus, an important model for studying how viruses assemble. Using the same X-ray diffraction techniques she had perfected in her DNA research, she captured detailed images of viral structures. Her findings provided crucial insights into virology, helping scientists understand how viruses replicate and spread. She collaborated closely with Aaron Klug, a brilliant young researcher who would later continue her work after her passing. While she thrived at Birkbeck, the scientific world continued to celebrate Watson and Crick. Their double helix model was immediately recognized as one of the most significant discoveries in biology. They received invitations to conferences, awards, and widespread acclaim. Watson, in particular, became a public figure, known for his sharp intellect and ambitious personality. Meanwhile, Rosalind worked quietly, avoiding the limelight. Her focus was on science, not recognition. But behind the scenes, she was well aware of how her work had been used without her permission. She confided in close colleagues, expressing her disappointment in how things had unfolded. Yet, she never publicly criticized Watson, Crick, or Wilkins. Instead, she poured her energy into her research, determined to make new discoveries. Her work on virus structures quickly gained international attention. She traveled frequently, presenting her findings at scientific conferences, earning the respect of researchers in the growing field of virology. While Watson and Crick had taken credit for DNA, Rosalind was pioneering new frontiers in biological science. However, as she reached new heights in her career, her health began to decline. In 1956, she started experiencing severe abdominal pain. Tests revealed devastating news. She had ovarian cancer. Many speculated that her years of exposure to X-ray radiation may have contributed to the illness, but there was no way to be certain. Despite the diagnosis, she refused to stop working. Even as she underwent surgery and treatment, she continued her research, determined to finish her final projects. By the time Watson and Crick were being positioned as scientific icons, Rosalind was quietly battling a terminal illness. She knew she had little time left, but she remained dedicated to her work until the very end. Her research on viruses was advancing, and she wanted to leave behind a scientific legacy that would outlive her. She spent her final months ensuring that her findings would be preserved. She continued working with Aaron Klug, passing on her knowledge, knowing that he would later carry forward her discoveries. She attended conferences, presented her research, and remained active in the scientific community until she physically could no longer continue. On April 16, 1958, at the age of 37, Rosalind Franklin passed away. The world lost one of its most brilliant scientific minds far too soon. She had made contributions that would shape the future of molecular biology. Yet her greatest discovery had been credited to others. Even in death, her name remained largely absent from the DNA story. 4 years later, in 1962, James Watson, Francis Crick, and Maurice Wilkins were awarded the Nobel Prize in Physiology or Medicine for their discovery of the DNA double helix structure. Rosalind Franklin's name was not mentioned, since the Nobel Prize is not awarded posthumously. She was ineligible for recognition. But many believed that, had she lived, her contributions would have been impossible to ignore. Though her life was cut short, her impact on science was undeniable. Her DNA research, though largely uncredited, had laid the foundation for one of the greatest discoveries in biology. Her virus research would continue to influence the field for decades. The world had overlooked her contributions, but history would not forget her forever. Over time, scientists, historians, and biographers would begin uncovering the truth. Her name, once overshadowed, would slowly rise to its rightful place in the story of DNA. Her journey was far from over. The fight for her recognition was just beginning. In 1962, James Watson, Francis Crick, and Maurice Wilkins received the Nobel Prize in Physiology or Medicine for their discovery of DNA structure. The world celebrated them as pioneers, the men who had unlocked the secret of life itself. But Rosalind Franklin's name was absent from the honor. She had died 4 years earlier, and the Nobel Prize was not awarded posthumously. However, this rule alone did not fully explain why her contributions had been ignored rather than recognized. Even before her passing, her role in DNA's discovery had been minimized. Watson and Crick had built their model using her data, yet they had not included her as a co-author or even acknowledged her as a direct contributor. In their Nobel acceptance speeches, neither Watson nor Crick gave her credit for the critical X-ray diffraction work that had provided them with the final proof of the double helix structure. Maurice Wilkins, who had worked alongside her at King's College, also did not publicly acknowledge her contributions. Her work had been essential, yet she had been erased from the most prestigious recognition in science. The question remained, if she had lived, would she have shared the Nobel Prize? Many scientists believed she would have been included, given the overwhelming evidence of her role in the discovery. Others argued that the scientific establishment, heavily dominated by men, may have continued to exclude her. The truth would never be known. But what was clear was that her contributions had been unfairly sidelined. Adding insult to injury, James Watson played a key role in shaping how the world remembered Rosalind Franklin. In 1968, he published The Double Helix, a personal account of the discovery of DNA. Rather than portraying Franklin as the brilliant scientist she was, he depicted her as difficult, stubborn, and unable to understand her own data. He even mocked her appearance, reinforcing the sexist attitudes that had marginalized women in science for centuries. The book became widely read, further distorting the narrative of how DNA's structure had been discovered. Watson's portrayal was met with outrage from those who had known Rosalind personally. Many of her colleagues, including Aaron Klug, defended her legacy, arguing that she had been misrepresented. But the damage had already been done. For years, the double helix was one of the most widely referenced accounts of DNA's discovery. cementing a false history in the public's mind. It would take decades before the truth about Rosalind's role was fully brought to light. Despite the erasure of her contributions, her scientific impact continued to grow. Her work on virus structures, conducted at Birkbeck College in the last years of her life, led to major advancements in virology. She had studied how viruses assembled and replicated, providing insights that would later contribute to modern vaccine development. Her collaborator, Aaron Klug, built upon her findings and went on to receive the Nobel Prize in Chemistry in 1982. Though she did not live to see it, her influence on molecular biology continued to shape the field long after her death. As the years passed, more scientists and historians began to re-examine her role in the DNA discovery. The injustice of her exclusion became increasingly clear. Biographers and researchers worked to correct the historical record, challenging Watson and Crick's version of events. By the 1980s and 90s, Rosalind Franklin's name began to emerge from the shadows. Her story was no longer just about DNA. It had become a symbol of the struggles faced by women in science. The more people learned about what had happened, the more her legacy grew. The scientific community began honoring her contributions, naming awards, research centers, and fellowships after her. The world was finally beginning to acknowledge the brilliance and perseverance that had defined her career. However, the question remained, why had it taken so long for her to receive recognition? The answer lay in a system that had historically overlooked the work of women scientists, dismissing their discoveries or crediting them to their male colleagues. Rosalind Franklin was not the first woman to experience this injustice, and she would not be the last. But her story had ignited a conversation that could no longer be ignored. Though the Nobel Prize had eluded her, her contributions could no longer be denied. The very structure of DNA, the discovery that revolutionized modern biology, was built upon her work. Her name, once nearly forgotten, was now being restored to its rightful place in scientific history. But the battle for her recognition was not over yet. Her legacy was still evolving, and the world was not finished rewriting her story. In the decades following Rosalind Franklin's death, the scientific world slowly began to reevaluate her role in the discovery of DNA. For years, Watson and Crick had been credited as the sole architects of the double helix model, with Maurice Wilkins recognized for his supporting work. But as historians and scientists revisited the events leading up to their breakthrough, it became increasingly clear that Rosalind Franklin had been instrumental in the discovery. By the 1970s, a shift in perspective had begun. More women were entering the fields of science and academia, and many of them looked to the past, uncovering stories of female scientists who had been overshadowed. Rosalind Franklin's story was one of the most glaring examples of how a brilliant woman had been denied the recognition she deserved. Historians started questioning how Watson and Crick had obtained the final proof for their model. How had they confirmed their structure so quickly after struggling for months? The answer pointed directly to Photo 51. Aaron Klug, who had worked closely with Franklin in her later years, became one of the most vocal advocates for restoring her legacy. He spoke openly about her groundbreaking contributions, emphasizing that without her precise X-ray diffraction work, Watson and Crick could not have built their model. Other scientists began acknowledging what had long been hidden. Her data had been used without her knowledge, and her contributions had been buried. By the 1980s, books and articles about Franklin's work started to challenge the official narrative. The myth of Watson and Crick as the sole discoverers of DNA was slowly unraveling. Scientists and scholars argued that her paper in Nature should have been given equal importance, rather than being treated as a supporting piece. Some even suggested that, had she lived, she might have been included in the Nobel Prize. forcing the world to acknowledge her contributions in a way that history had denied her. One of the most significant turning points came in 1997, when author and Sayer, a close friend of Franklin, published Rosalind Franklin and DNA. The book directly confronted the way Watson had portrayed Franklin in the double helix and exposed the misrepresentations that had shaped the public's perception of her. Sayer's work challenged the sexist biases that had played a role in Franklin's erasure from history, making it clear that she had been an equal contributor to the DNA discovery. Over time, more books and documentaries followed, each further cementing her rightful place in the history of science. The world was beginning to understand that Rosalind Franklin had not merely provided data. She had uncovered the key to DNA's structure. She had worked tirelessly, driven by scientific integrity, never seeking fame or recognition. Yet, her work had made possible one of the greatest discoveries in molecular biology. As the 21st century began, universities, institutions, and scientific organizations started honoring her memory. The Rosalind Franklin University of Medicine and Science was established in the United States, a major step toward ensuring that her name would never be forgotten. Fellowships, research awards, and institutes bearing her name appeared across the world, acknowledging the impact of her work on molecular biology and virology. In 2002, biographer Brenda Maddox published Rosalind Franklin, The Dark Lady of DNA, a definitive account of her life and contributions. The book shed new light on the struggles she faced as a woman in science, the betrayal she endured, and the remarkable discoveries she made despite these challenges. Maddox's work helped bring Franklin's story to an even wider audience, ensuring that her legacy would be understood by future generations. Today, Rosalind Franklin is no longer a forgotten scientist. Her contributions to DNA's discovery are recognized in textbooks, classrooms, and laboratories around the world. The injustices she faced cannot be undone, but her name now stands alongside Watson, Crick, and Wilkins, not as a footnote, but as an essential part of the story. Though she never sought fame or recognition, history has finally corrected its course. Her work, her perseverance, and her brilliance continue to inspire scientists, especially women, who follow in her footsteps. And while Watson and Crick may have received the prize, the truth about who truly unlocked the structure of DNA will never be forgotten again. After leaving King's College London in 1953, Rosalind Franklin turned her attention to a new scientific challenge. Though her contributions to the DNA discovery had gone unrecognized, she was not the type to dwell on past injustices. She accepted a research position at Birkbeck College in London, where she would begin pioneering work in a new field, virus structure. Her expertise in X-ray diffraction made her the perfect candidate to study how viruses assemble and function. She applied the same meticulous techniques she had used in her DNA research, capturing detailed images of viral particles at the molecular level. Her focus was the tobacco mosaic virus, an important model for understanding how viruses reproduce and spread. Her findings would later become foundational for modern virology, influencing studies on everything from influenza to coronaviruses. Working under John Bernal, a respected figure in crystallography, Franklin was finally in an environment where she was respected as an independent scientist. Unlike at King's College, where she had faced rivalries and betrayals, Birkbeck College allowed her to lead her own team. She collaborated closely with Aaron Klug, a young researcher who would later continue her work and go on to win a Nobel Prize for studies in molecular biology. Her work on viruses provided key insights into how genetic material is stored within viral structures. She discovered that the tobacco mosaic virus had a helical structure, similar to DNA, with its genetic material wound inside a protective protein shell. This was a groundbreaking revelation, helping scientists understand how viruses infect cells and replicate. Her research laid the groundwork for future vaccine development, proving essential in the fight against viral diseases. In the mid-1950s, she expanded her studies to include the poliovirus, a major public health concern at the time. Polio was a devastating disease, causing paralysis and death worldwide, and Franklin's research provided crucial structural data that helped scientists develop effective vaccines. Though she did not live to see it, her work played a role in the eventual eradication of polio in many parts of the world. Even as her scientific reputation grew, her health began to decline. In 1956, she started experiencing severe abdominal pain. Tests revealed a devastating diagnosis: ovarian cancer. Many speculated that her prolonged exposure to X-ray radiation without proper protective measures may have contributed to her illness, but there was no way to know for certain. Despite undergoing multiple surgeries and chemotherapy treatments, she refused to slow down. Even as she battled cancer, she continued working in the lab, pushing forward with her virus research. She traveled to the United States to present her findings, attended conferences, and collaborated with leading virologists. Her determination was extraordinary. Even in the face of a terminal illness, she remained dedicated to science. By 1957, her condition had worsened, but she kept working for as long as she could. She mentored Aaron Klug, passing on her knowledge so that he could continue her work after she was gone. She ensured that her findings would not be lost, leaving behind meticulously detailed research notes and papers. She was determined that, even if she did not live to see the impact of her work, her discoveries would continue shaping the future of science. On April 16, 1958, Rosalind Franklin passed away at the age of 37. Her life had been tragically short, but her contributions to science had been immense. She had made major discoveries in DNA, coal structure, and virus crystallography. Yet her name was still not widely recognized outside scientific circles. Though she did not live to see the full impact of her work, her contributions to virology would continue to influence generations of scientists. Her research on viral structures became essential for understanding how diseases spread and how vaccines could be designed. The techniques she developed for studying viruses using X-ray diffraction became standard practice in molecular biology. 4 years after her death, Aaron Klug expanded on her research, eventually leading to his Nobel Prize in Chemistry in 1982. Though Franklin had not lived to receive such recognition, her work had made his discoveries possible. In a way, her legacy lived on through the scientists she had mentored and inspired. Today, her contributions to virology are considered just as important as her work on DNA. While she is often remembered as the uncredited scientist behind the DNA discovery, her work in virology has had just as profound an impact on the medical field. Without her insights, modern vaccine development and antiviral research would not be where they are today. Her legacy was still unfolding, and the world was finally beginning to realize just how much science owed to Rosalind Franklin. But there was still more work to be done in ensuring that her name was properly honored. Her contributions to molecular biology, genetics, and virology had shaped the future of medicine, and it was time for history to give her the recognition she had been denied in life.
When developed,
Rosalind Franklin's scientific achievements remained overshadowed for years after her death. While Watson and Crick became household names, her contributions to DNA's discovery and virology were only acknowledged in scientific circles. But as time passed, historians, biographers, and researchers began uncovering the full extent of her impact. Slowly, institutions, universities, and scientific organizations started recouzing her contributions, ensuring that her name would not be forgotten. One of the most significant honors came in 1982, when Aaron Klug, one of Franklin's closest collaborators, received the Nobel Prize in Chemistry for his work in crystallography. His achievements built directly upon the foundation that Franklin had laid, particularly her studies on virus structure. Though she had not lived to see it, her influence was undeniable. Without her research, his breakthroughs would not have been possible. Klug, unlike Watson and Crick, was one of the few to openly acknowledge the critical role that Franklin had played in advancing molecular biology. By the 1990s, awareness of her contributions had grown, and institutions around the world began honoring her name. In the United States, the Rosalind Franklin University of Medicine and Science was established, focusing on medical research and scientific education. This was a major step in ensuring that her legacy lived on, providing opportunities for future generations of scientists, especially women in STEM fields. Universities and laboratories also began naming buildings, research centers, and awards after her. The Rosalind Franklin Laboratory in the UK, established to help combat infectious diseases, was named in her honor, reflecting the enormous impact her virus research had on modern medicine. The Royal Society, one of the most prestigious scientific institutions in Britain, established the Rosalind Franklin Award, recognizing outstanding contributions by women in science. Beyond official institutions, Franklin's story inspired generations of female scientists. Many saw her as a symbol of perseverance, someone who had fought against discrimination and injustice while remaining completely dedicated to her work. Her name became associated with scientific excellence, determination, and integrity. Her impact was also recognized in space exploration. NASA named the Rosalind Franklin rover part of the ExoMars mission after her. The mission, set to explore the surface of Mars, was a testament to how her influence had extended beyond biology into the realm of space exploration. The decision to name the rover after her was symbolic. It honored not only her contributions to science, but also the long-overlooked women in STEM who had made groundbreaking discoveries throughout history. In addition to these honors, her story has been featured in countless books, documentaries, and films, ensuring that future generations learn about her work. The Dark Lady of DNA, a biography written by Brenda Maddox, played a crucial role in reshaping public perception of Franklin's contributions. The book exposed the injustices she faced, correcting the narrative that had long downplayed her role in the discovery of DNA. While official recognition took decades, her name was now firmly embedded in scientific history, no longer just a footnote in the story of DNA. She was finally receiving the credit she had always deserved. But more than awards and honors, her real legacy lay in the impact of her research. The DNA double helix model remains the foundation of genetics, medicine, and biotechnology. The X-ray diffraction techniques she pioneered are still used in structural biology and medical research, and her work in virology has influenced vaccine development and the fight against emerging diseases. The scientific world had taken far too long to recognize her contributions, but history was finally correcting itself. Rosalind Franklin's name, once nearly erased, had now become a symbol of scientific brilliance and perseverance. Though she did not live to see it, her work had changed the world, and the institutions bearing her name would continue her legacy for generations to come.
Rosalind Franklin was born in London in 1920, into a family that achieved
Rosalind Franklin's pioneering research did not just contribute to one historic discovery. It laid the foundation for countless advancements in genetics, medicine, and biotechnology. The DNA double helix model, built upon her X-ray diffraction images and structural insights, became the cornerstone of molecular biology. But the true impact of her work only became clearer as DNA research continued to evolve. In the decades after DNA structure was identified, scientists unraveled the genetic code, discovering how DNA sequences controlled biological traits, hereditary diseases, and evolution. This breakthrough led to genetic engineering, cloning, and gene
Her
therapy,
parents sent her to
all of
St.
which
Paul's
relied on
Girls'
the
School,
understanding of
which,
DNA
despite its
structure
name,
that
had
Franklin's
no
work
church
had made
affiliation.
possible. Though
What
Watson
it
and
did
Crick
have
became
was
the
a
public
strong
faces of
tradition
these
of preparing
advancements,
girls for a
every
career.
breakthrough in molecular
Sue
genetics was
Richley
built
and Ann
upon the
Piper
data she
attended
had
St.
first
Paul's
uncovered.
and were
One of
Rosalind
the most
Franklin's
significant
lifelong
projects
friends.
that benefited from
She
her
was
work
the
was
best
the
at
Human
science, she
Genome
was the
Project,
best at maths,
an
and she
ambitious
was just
initiative launched in
one of the best
1990.
in that.
The project aimed to map
The
all
best, I
human
would say, in
genes,
that, yeah.
providing
She played
an
in the
unprecedented
teams.
understanding of
Talking
genetic
across
diseases and human
the
biology.
apple,
The ability to
she
sequence and
combined
analyze
using her
DNA
mind
relied on
play
techniques that
with
were direct
having a
descendants
certain
of
natural
Franklin's
ability.
X-ray diffraction
She
methods.
always expected
Though she had not
that if
lived
she
to see
undertook
it,
something,
her
she would
research
be
had
running
directly
it.
contributed to one of the
She
greatest
wished
scientific
to be
achievements of the
expected
21st
to be
century.
like that.
Her influence
Yes.
extended beyond genetics into
While
medicine and
Rosalind
disease
excels
research.
academically,
The ability
the
to
outside
analyze
world is
DNA
encroaching.
and viral
The
structures,
Nazis are on
something
the
she had
march.
pioneered in her later years, became crucial
As
for
Jewish
diagnosing
refugees
and
flee
treating
the Nazi
genetic
onslaught,
disorders.
the Franklins
Today,
are active
diseases
in
like
finding
cystic
safe haven
fibrosis,
in England
sickle cell
for those who
anemia,
manage to
and
escape.
Huntington's disease can be better understood and treated
Rosalind
because
is
of her
anxious
contributions
to do
to
something
DNA
useful with her
science.
life.
Perhaps most
She finishes
importantly,
a year early at St.
Franklin's
Paul's
research
and
methods
wins a
have
scholarship
continued to
study
influence
physics and
structural
chemistry
biology
at
and
Cambridge
virology.
University.
The same X-ray diffraction techniques she used to
1938,
analyze the
Rosalind
tobacco
arrived
mosaic
here
virus
at
are
Newnham
now
College,
used to
one of
study
the women's
viruses like
colleges at Cambridge
HIV,
University.
influenza,
In
and
her classes, she's
coronaviruses.
introduced to the
During
new
the
subject of
COVID-19
X-ray
pandemic,
crystallography.
researchers relied
This
on methods
technique
similar
can
to
reveal
those
the hidden
Franklin
atomic
developed to
structure of
analyze
matter
the
in
virus's
its
genetic
crystalline
structure
form.
and design vaccines.
Atoms
Though
are
she
too
passed
small
away
to see
decades
under light
earlier,
microscopes,
her scientific legacy was
crystallographers
directly
shoot invisible
influencing the
X-rays
fight
at them,
against modern
which then
diseases.
bounce off or
Her
diffract
work has also
onto
played a
detector
role
such
in
as
forensic
film.
science, evolutionary
By applying
biology,
math
and
to the diffraction
biotechnology.
pattern,
The
it's
ability to
possible
analyze
calculate
ancient
the
DNA from
three-dimensional
fossils,
form of even the
track
most
human
complex
migration through
molecules.
genetics, and develop DNA-based computing
In her
all
X-ray
stem from the
diffraction work,
fundamental
Rosalind
understanding
joins
of
the small
DNA
band of the
structure,
human race for
a
whom
discovery
tiny
rooted in
specks of
Franklin's
matter are as real
research.
as billiard
Every
balls.
new advancement in genetics and molecular biology
In
owes something to the
1939,
X-ray
as
images she
Franklin
took,
steps into the
the
world
data
of
she
science,
collected, and the
Cambridge
techniques she
University appoints
perfected.
its first female
Despite
professor,
all these contributions,
and Britain
her name
prepares
is
for the
still
German
not as
invasion.
widely recognized as Watson and Crick's.
By the time she
Textbooks
graduates,
often mention her
Franklin
only
is determined
briefly,
to contribute
and
to
many
the war
students
effort.
learning about DNA structure never hear the
Her
full
father
story.
pressures her to
But
carry on the
efforts to
family's
correct
charitable
the
tradition.
historical record have
She
continued
replies
to grow.
that she would be of little
Scientists,
use in anything but
educators,
science.
and biographers have worked
When he
tirelessly
accuses her of
to
making
ensure that
science her
future
religion,
generations
he writes,
understand the true
"In my
impact
view,
of her work.
all that is
Though she
necessary
did not
for faith
receive the Nobel
is the belief
Prize,
that by
her
doing our
influence
best,
extends
we shall
far beyond
succeed in
any
our
award.
aims.
The discoveries she
improvement of
enabled have
mankind.
transformed medicine, biotechnology, and our understanding of life itself. DNA research is still evolving,
Cambridge really did for
and with
Rosalind
every
everything
breakthrough
that a
in
good
genetics,
university should.
her
It
legacy
gave her a
continues
profession,
to
a
shape the
philosophy
future of
life.
science.
It enabled her to
She was
distance
more than
herself
just
from
a
her
brilliant
parents.
scientist.
She emerged a mature,
She was a pioneer whose
socially
work
and
will
politically
continue
aware
to impact the
individual,
world for centuries to
and
come.
she was ready to become a working scientist.
She joined the war effort doing research on
Rosalind
coal.
Franklin's
Her
journey was not
experiments
just
led
a
to better
story of
gas
scientific
mask, a
discovery.
valuable contribution
It was
to
also a
England under
reflection
attack.
of the struggles faced by
She
women
published
in
5
science.
landmark papers,
Her brilliance
still
and
cited
dedication
today,
were
and she was
undeniable.
awarded her PhD.
Yet throughout her career,
When
she
the war
faced
was
barriers
over,
that her male
experience
counterparts
earned her
did
the
not.
job offer of
The
her
challenges
dreams,
she encountered,
a research
from
position
being
in one
treated
of the
as a
best
mere
labs in
assistant to
Paris.
having her data used without her knowledge, highlighted the systemic biases that kept
One of her
women from
closest
receiving
colleagues
full
and friends at the
recognition for their work.
laboratoire
Her
is
story is
Vittorio
not
Rosati.
unique.
Here in a
Throughout
restaurant
history,
that Rosalind
many
enjoyed.
female scientists have made groundbreaking
She
discoveries,
loved Paris.
only to have
She
their
loved
work
life in
overlooked,
Paris. That was
dismissed,
quite clear.
or credited
She was
to male
very
colleagues.
happy here.
Women like Lise Meitner,
She
Jocelyn
took a flat
Bell
on a
Burnell,
little street
and
behind
Nettie
the
Stevens
Church of
all made
Saint-Sulpice
major
in the
contributions to
6th
science, but were
arrondissement.
either denied Nobel Prizes or
She wore
had
the
their work
latest in
overshadowed
Paris
by
fashion.
men.
Dior's
Franklin's
new look
experience was
for the
part
new
of a
woman.
larger pattern, one that persisted for decades
She
and
shopped
still
in the
exists
fresh air
in some
markets
forms
and
today.
took great pleasure cooking
Despite
for
these
her
challenges, Franklin never
She walked
sought
to work along the
recognition or
Seine,
fame. fame,
passing in
she
the
was
shadow
not
of
concerned
Notre
with
Dame to the
rivalries or
Laboratoire
professional
Central
politics.
at 12
She cared
quai
only
Henri
about
IV.
scientific integrity and the pursuit of
It was
knowledge,
here, in a
She
collegial
refused to be
atmosphere
anything less
that
than
Franklin
meticulous
perfected
in her
her
research,
techniques of X-ray
even when
diffraction.
others around her rushed to publish incomplete conclusions. She set an example for future scientists by showing that rigor, patience, and dedication mattered more than personal ambition. Her story has since become a rallying cry for women in STEM fields, inspiring countless young scientists to pursue careers in physics, chemistry, and biology. Over the years,
Franklin was
initiatives
gaining an
aimed at
international
increasing
reputation,
female representation
speaking at
in science
conferences
have
and
gained
publishing in
momentum,
professional journals.
with Franklin's story often cited as a
An
reason
avid
why
hiker, she took
diversity
trips
and
with
inclusion
colleagues
in
to
scientific
Norway,
research
Wales,
must be
and the Alps.
prioritized. The Rosalind Franklin Award, established by the Royal Society,
Her research
now
was not without
recognizes
its risks.
outstanding women in science,
Lab
ensuring
workers
that
were
her legacy
periodically checked
continues
for
to empower
overexposure to
future
X-rays.
generations.
And
Her
when
name
Franklin
has also
exceeded safe
become
levels,
synonymous
she
with
was upset
perseverance,
that she had to stay away
excellence,
from the lab
and
for a few
justice in
weeks.
scientific recognition. Every time a new discovery is credited properly to the
After
woman
4
behind
years
the
in
research,
Paris, she
it is a
faced
step
decision.
toward correcting the
Should she stay
historical
in France
injustices that
or
Franklin
return home
and
to
others
England?
faced. Though she never lived to see it,
She asked the
the
advice
fight
of
for
Dorothy
fairness in
Hodgkin,
science
a
has
renowned
continued in her name.
crystallographer and one of
Today,
only 10
women
women
in
to
molecular
win a Nobel
biology,
Prize.
genetics, and virology stand on the foundation
And it
she
was
helped build,
Dorothy's
conducting
advice
research that
that
would
it
not
was
have been possible
time
without
for
her
her
work. Every
make
new
up her
generation of
mind,
scientists
and
who
if
learn
she
her story
decided
see her
to
not just as a
have a
scientist who was
scientific
denied
life
credit,
in England,
but as a
she should go
pioneer
back.
who changed science forever.
And she left
Her
reluctant.
legacy
She was
serves
not
as a
very happy to
reminder
leave
that scientific
Paris. I
progress
think that
should be measured not by who gets the most
decision she
recognition,
had to make, and it
but
was
by the
to some extent
discoveries
a
that
cruel
changed
one.
the world. Though she was overlooked
Franklin
in her
is offered a
time,
position at King's
history has
College in
finally
London,
placed
a
her in the
highly
pantheon of
prestigious
great
research
scientists
center.
where she always belonged.
She is hired
Her
by J.T.
contributions
Randall,
continue to
the
shape
director
modern
of the
science,
biophysics labs,
proving
to
that
create
true
an X-ray
pioneers do not
diffraction
need
unit
awards
to
to leave an
investigate the
impact
structure
that
of
lasts
proteins.
forever.
She accepts the offer, but writes to a friend to change the
One of the
banks
most
the Seine
persistent
for a
questions
cellar on the
surrounding
Strand
Rosalind
seems
Franklin's
to me
legacy is
quite
whether she would have
insane.
shared the Nobel Prize if she had lived. The
But as
Nobel
she is
Prize
leaving
in
Paris,
Physiology
she
or
receives a
Medicine was
letter from
awarded in
Randall,
1962
shifting
to
her
James
focus from
Watson,
proteins
Francis
to the
Crick,
little understood
and Maurice
substance
Wilkins
called
for their
DNA.
discovery of DNA's double helix structure. But by
Rosalind
that
Franklin
time,
is 30
Franklin
years
had been
old
dead for
as
4
she
years,
unwittingly enters
making her
an
ineligible for
undeclared
the
race
award under
to
Nobel
unravel
rules,
the secret
which do
of
not
life.
allow posthumous recognition. Many scientists and historians believe that if she had survived, she would have been included in the Nobel Prize alongside Watson, Crick, and Wilkins.
So this
Her
is
work
DNA.
was essential to the discovery,
Really beautiful
and
and
Photo
amazing
51
stuff.
provided the final proof
Responsible
of
for
DNA's
heredity,
helical structure.
the genetic material.
Without her precise X-ray diffraction
Some would argue that
images,
it's the blueprint
Watson
for every
and
cell in
Crick
your
would have
body.
continued struggling to confirm their model. Her contribution was
At the time
not
when Rosalind
secondary.
Franklin started
It was
working
the
on
crucial
DNA,
piece of
it wasn't
evidence.
at all clear
However,
what DNA
others
really looked
argue
like
that even
or
if
how it
she had
might work.
lived, she might still have been excluded. At the
In
time, women were
1943,
rarely
after a
awarded
decade of
Nobel
work,
Prizes,
Oswald
and
Avery
institutional
and his team at
biases were
Rockefeller
deeply
University
entrenched in the scientific
transferred
community.
DNA from a
It was common for
disease-causing
women's
strain of
work to be
bacteria
overlooked in
into a
favor
harmless
of their
strain.
male colleagues.
The
And the
harmless strain
politics of the
turned
King's
virulent,
College and Cambridge
strongly
research
suggesting a
teams
link
may have
between
resulted in her
DNA
being
and
sidelined.
heredity.
Even if she had been alive, Watson,
Avery's
Crick,
experiments
and
showed
Wilkins
that
never
genetic
publicly
characteristics
campaigned
of
for
one
Franklin to
organism
be
could
included,
transferred to another.
even after her
And he
death.
showed that DNA
In their
was the
Nobel
vehicle
Prize
of that
speeches,
transformation,
they
that
did
DNA
not
was the
acknowledge
genetic
the full
material.
extent of her
But that conclusion
contributions,
was by no means
reinforcing the
universally accepted.
narrative that she had only played a supporting
DNA
role.
was thought to
If even in
consist of
death her
sugar
work
and
was
phosphates
downplayed,
in long
it is
chains
possible
of
that
some
she would not
unknown
have been
shape.
awarded the Nobel Prize at all.
It also
But
appeared
the
to have
reality
just
is
4
that
other
awards
chemical
and
ingredients
prizes were
called
never what
bases.
drove Franklin. Throughout
But
her
how could
career,
such a simple molecule
she was
be
motivated by the
responsible for
pursuit
the
of
diversity
scientific
all
truth,
life on Earth?
not recognition. She refused to
Some
rush her
believed that
research for the
discovering
sake of
structure
being first.
DNA would
She
lead to an
believed in
answer.
methodical, rigorous work, ensuring that
That
her
was Franklin's
conclusions were
assignment
accurate
when
and
she arrives at
irrefutable.
King's College,
She might
London
not have
in
cared
January
about the political
1951.
games that often determined who received awards and who was
Now
left
a
out.
professor at King's,
Even though she never
Raymond
won a
Gosling
Nobel
was a
Prize,
PhD student
her
in
contributions
biophysics
to
at
DNA,
the time of
virology,
Franklin's
and
arrival.
molecular biology have had a greater impact
first
than
came
any award could
in,
symbolize.
49,
In the
50,
end, her
what there
legacy was not dependent
was a
on
bomb
medals or
crater.
recognition. Her work
Remains of
continues
the
to shape
Second
the
World
future
War.
of science. Today, she is recognized not as a scientist who was denied an award, but as a pioneer who changed the course of history. The Nobel Prize may have overlooked her, but history has not.
Our physics department was done.
Rosalind Franklin's name is now synonymous with perseverance, scientific excellence, and a fight for rightful recognition. Though she did not live to see her contributions fully acknowledged, history has slowly corrected itself, and today she is remembered as one of the most important scientists of the 20th century. Her story is no longer just one of overlooked achievements. It is a testament to the fact that true scientific discovery transcends personal recognition and fame. The structure of DNA, the blueprint of life itself, remains one of the most groundbreaking discoveries in biology. Every advancement in genetics, medicine, and biotechnology is built upon that knowledge, and Franklin's Photo 51 was the crucial evidence that made it possible. Without her meticulous work, Watson and Crick's model might never have been completed. Her research provided the experimental foundation upon which the entire field of molecular biology was built. Beyond DNA, her contributions to virology have shaped modern medicine. Her X-ray diffraction techniques, first applied to coal and graphite, later became instrumental in the study of viral structures. The very same methods she used to analyze tobacco mosaic virus are now used to understand emerging diseases like COVID-19, Ebola, and HIV. The field of structural virology owes much of its progress to the techniques she developed. Today, her influence is seen in scientific institutions, educational programs, and research initiatives. The Rosalind Franklin University of Medicine and Science stands as a lasting tribute to her contributions, fostering the next generation of researchers. The Royal Society's Rosalind Franklin Award ensures that her name is forever associated with scientific excellence and the advancement of women in science. Perhaps the greatest measure of her impact is the number of scientists she has inspired. Every young researcher who picks up a crystallography study, every woman who enters a male-dominated scientific field, and every scientist who believes in the importance of precision and integrity is following in her footsteps. She may have been denied credit in her lifetime, but today, her legacy is far greater than any award or prize. Her story is a reminder that history does not always recognize greatness in the moment. Sometimes, it takes decades for the truth to be fully acknowledged, but in the end, scientific discoveries are not about who gets the most recognition, but about the knowledge they bring to humanity. Rosalind Franklin's work changed the world, and though her name was once left out of the DNA discovery, it will never be forgotten again. For many years, Rosalind Franklin's contributions to science remained in the shadows of Watson and Crick's fame. While their names became synonymous with the discovery of DNA structure, her role was largely unknown to the public. But over time, historians, scientists, and advocates began to reconstruct the true story, challenging the traditional narrative and ensuring that her contributions were no longer ignored. A turning point came in the 1970s and 80s, as women in science movements gained momentum and researchers revisited cases of overlooked female scientists. Franklin's story became one of the most striking examples of how gender bias had shaped scientific recognition. Historians uncovered how her data had been used without her permission, how she had been excluded from the race for DNA's discovery, and how Watson's portrayal of her in the double helix had distorted the truth. Aaron Klug, one of Franklin's closest collaborators, was one of the first to publicly defend her reputation. He emphasized that Franklin had fully understood her data and had been on the verge of drawing the same conclusions as Watson and Crick. He also revealed that Franklin had been working on an alternative DNA structure that could have advanced molecular biology in new directions. Her work was not just a stepping stone for others, It was a
articulate,
major
passionate,
breakthrough
and
in
always
its
up
own
for a
right.
good debate.
The 1990s and early
soft-spoken,
2000s saw
deliberate,
an
and
explosion
shy,
of books,
just couldn't get along.
documentaries, and academic studies focused on reclaiming her legacy. The publication of Rosalind Franklin and DNA by and Sayer and The Dark Lady of DNA by Brenda Maddox helped the world see her as a brilliant scientist in her own right rather than as a victim of scientific politics. These books exposed the misrepresentations in Watson's accounts and revealed how much of DNA's discovery had relied on her meticulous research. Documentaries and television specials began featuring Franklin's story, showing how her perseverance, intellect, and dedication had led to one of the greatest scientific discoveries of the 20th century. Schools and universities began including her name alongside Watson and Crick when teaching about the discovery of DNA, ensuring that future generations would learn the full story. Beyond recognition, her legacy inspired changes in how women were treated in science. Her story became a symbol of the challenges women faced in male-dominated fields, fueling efforts to increase female representation in STEM disciplines. Organizations dedicated to supporting women in science began using Franklin's story as an example of why the scientific community needed to be more inclusive and equitable. As her reputation was restored, institutions around the world named buildings, research programs, and fellowships after her. Her contributions to DNA research, virology, and structural biology were recognized as foundational to modern science. No longer a forgotten scientist, Rosalind Franklin was finally acknowledged as a pioneer whose work changed the world. Though it took decades, history had finally corrected its course. But one final question remained. How would Rosalind Franklin herself have viewed all of this recognition? Would she have wanted to be remembered as a scientific martyr, or as a brilliant researcher who let her work speak for itself? The answer lies in the way she lived her life, dedicated, fearless, and always moving forward. She may never have sought fame, but her name is now immortalized in the history of science. And with every new discovery in genetics, molecular biology, and virology, her influence continues to shape the future.
There, Watson is assigned an office with another
Today,
physicist turned
Rosalind
crystallographer,
Franklin is
Francis
recognized
Crick,
as one
an
of the
old
most
friend of
influential scientists of the 20th century.
Crick and Watson
Though she was denied
immediately
recognition in her lifetime, her impact on genetics, molecular biology, and virology has only grown stronger over the decades. Her work, once overshadowed by Watson and Crick, is now acknowledged as foundational to the discovery of DNA's double helix structure. Her research on viruses has become even more relevant in the 21st century, influencing the development of vaccines and treatments for emerging diseases. Franklin's legacy extends far beyond DNA. Her X-ray diffraction techniques are still widely used in structural biology, helping scientists understand the structures of proteins, viruses, and new drug compounds. The same methods she used to study coal and graphite are now used to develop nanotechnology, medical imaging, and material science. She was not just a contributor to one field. She was a pioneer in multiple areas of science. One of the greatest testaments to her impact is the way her name has been immortalized. The Rosalind Franklin University of Medicine and Science, the Rosalind Franklin Institute in the UK, and countless fellowships, awards, and research programs now bear her name. Her contributions have also reached beyond Earth itself. The Rosalind Franklin rover, part of the European Space Agency's ExoMars mission, was named in her honor, ensuring that her legacy extends into space exploration. Her story has also transformed how women in science are viewed and supported, the challenges she faced, being dismissed, excluded, and denied recognition, are reminders of how women have had to fight for their place in scientific history. But her legacy has inspired generations of female scientists to pursue careers in STEM, ensuring that future breakthroughs will come from a more diverse and inclusive scientific community. Beyond the scientific world, Franklin's
produces a
story has
simpler
entered
image,
popular
but reveals
culture.
a key clue
Books,
to solving the structure of
documentaries,
DNA.
films, and stage productions have brought
The
her
X
life
shape
and
in the
achievements to a
is the
wider
diffraction
audience,
signature
making
of a
sure that the
helix.
next generation learns about her work, her
The
struggles,
significance is
and her
not lost
ultimate
on
triumph.
Franklin.
She is no
notes
longer
it in
just a name
scientific
hidden
shorthand,
in
and
academic
according
papers.
to Klug, presents
She is
her
a symbol of
discovery.
perseverance, brilliance, and scientific integrity. The structure of DNA remains one of the greatest scientific discoveries of all time. But history now remembers that the discovery was not the work of just two men in Cambridge. It was the result of decades of meticulous research, of which Rosalind Franklin was a central figure. Every new advancement in genetics, medicine, and molecular biology is built upon her work, ensuring that her influence will continue to shape the world for centuries to come. Her life was
In the
short,
audience that day
but her
is
impact
James
is
Watson,
eternal.
sent
Though she
by
was
Crick
once
to gather
overlooked,
intelligence
her
on
name
Franklin's
is now
labors.
inseparable from the story of
Crick and
DNA
Watson
and
are
modern
planning to use
science.
a different approach
Rosalind
to solving the
Franklin's
structure of
legacy
DNA.
has been restored,
Model building.
and it will never be forgotten again.